Hi Michaela and Isabella, sorry I can't be there for this lesson on simple harmonic motion, but hopefully you've got the notes in front of you and you know that examples, I guess, of particles that move in simple harmonic motion are things like a pendulum or the rise and fall of a tide, things like that. So I'm going to model it really with things just going back and forth like that with my pen in the examples. So when a particle is in simple harmonic motion, it moves so that its acceleration is always proportional to its displacement from the origin. So acceleration equals k, which is going to be negative n squared times displacement there. When the equilibrium point is not the origin, when it's some other point x0, then this becomes the equation for the acceleration. And then you can say then that the displacement of the particle can be given by either this equation or this equation, where a, n, and epsilon are constants. A represents the period, the amplitude, and the period of motion is 2 pi and n, just like in 2 unit. So if we did the proof, starting with x equals a cos nt plus epsilon, differentiating that, you get this one. Differentiating again, you get the acceleration, and then just rearranging it so that you got negative n squared out, and then you can see a cos nt plus epsilon is what the displacement is, so just replacing that there. So then you can see that the acceleration equals negative n squared x, and you could do the same proof for x equals a sine, so we'll do it for this other one, x equals a sine nt plus epsilon, and so then the velocity equals na or an cos of nt plus epsilon, which means the acceleration is negative an squared sine of nt plus epsilon, and just rearranging, taking out the negative n squared, multiplying it by a sine nt plus epsilon, and you can see just there we have our displacement in the brackets. Okay, so just there is the displacement. Alright, so depending on what the question is, you may want to start with either that as your displacement equation or this. Okay, here's some other notes that I've got printed for you. So just remember, when a particle is moving in simple harmonic motion, it is just going back and forth like that for, I guess, the pendulum. And you can see with that, I guess, if the displacement from the origin is here, you can see if it's moving like that, right at the end point, so just here, the velocity is 0. When you get down to the origin here, the velocity is a maximum, and then back up here, the velocity is 0. Okay, so when the displacement is 0 right here, velocity is the maximum and also the acceleration is 0. When the velocity is 0 right here, displacement is a maximum and acceleration is a maximum, likewise at this point over here. And when acceleration is 0, that was back here, velocity is a maximum and displacement is 0. So when the particle moves towards the origin, velocity and acceleration are in the same direction, so when we're coming down this way, so the particle speeds up. But when the particle moves away from the origin, like up here, velocity is in the opposite direction to acceleration, so the particle slows down. Alright, in this first example, I've just put or scanned all my solutions and put them in, so I'm just going to be explaining them. Particle moves in a straight line and its acceleration is given by that. Show that x equals that is a possible expression for the particle's displacement. So starting with x equals 2 cos 3t, differentiate to find the velocity, differentiate again to find the acceleration, and then just rearrange it so that you can see in the brackets there is the displacement. And then we've just shown that that is the displacement, which represents the acceleration equals negative 9x, which was what was given. Find the maximum velocity and show that this velocity occurs when x equals 0. So max velocity occurs when the acceleration is 0. So make the acceleration equal to 0. You can see that's when x equals 0. Remember, right in the middle of our movement just here at the origin. So then subbing that into our equation of our displacement to solve for t, you get the first time, I guess it happens is at t equals pi on 6, but it's going to keep happening periodically, and then find the maximum velocity. So we want to find sub t equals pi on 6 into the equation for the velocity, and you get the max velocity is -6. If we were to sub in t equals 3 pi on 6, we'd get +6. So the max velocity is 6, depending on which direction you're talking about the particle moving. It's going to be -6 or +6, right down at the origin. Right, the next example, particle moves in a straight line such that acceleration equals -4x. So as soon as you see something like that where the acceleration is proportional to displacement, then you know it's going to be simple harmonic motion. The initial displacement is 5 meters. That means when t equals 0, x equals 5 meters. And initial velocity, so that means t equals 0, velocity equals 10. Find an equation for displacement in terms of time. So we're starting with our acceleration there. And remember, this was the equation we had for acceleration. So you can see that n squared equals 4, so n must equal 2. Alright, so there's our equation for our displacement. We're going to replace the n with 2. Then we're going to sub in our initial conditions to try and find, so we're going to sub in x equals 5, t equals 0, x equals 5, t equals 0, to get one equation there. We are also going to find an expression for the velocity, sub in t equals 0 there and velocity equals 10 there. Then we'll have two equations, this one here and this one here. So two equations, two variables. So we're going to do, I guess if you call this equation 1 and that equation 2, then to get this one here, we're going to do equation 2 divided by equation 1. That's why I've just written it equation 1 underneath, so I'm dividing 2 divided by 1. And we get tan echelon equals -1. And echelon actually ends up being -3 pi and 4, which is equal to -pi and 4. So just make sure your echelon is an acute angle there. Okay, so then you can just sub that back into either equation 1 or equation 2 to find your A, and you end up with A being 5√2. So it's just been, looks like it's been cut off a little bit at the bottom there. X equals 5√2 cos of 2t minus pi on 4. Alright, so we just had to find A, N and T. Next example, show that a particle with displacement that moves in simple harmonic motion and find its equilibrium and endpoints. Alright, so starting with our equation of our displacement, differentiating to find velocity, differentiating again to find acceleration, and just factorising out the 4 so that you have the 3 cos 2t in there, which was part of the original displacement equation. And then you can either do that two ways. You can say 3 cos 2t is 5 minus x, or a better way, I think, is rather than doing this line and this line, is changing the 12 into -4 times -3. And then you can say -3 cos 2t is equal to x minus 5, because then it is in the form given on the equation at the top of the first page of notes. And you can see then that 5 is the centre of motion. I remember the equation was acceleration equals -n squared x minus x0. So you can see the n squared is 4, so n must be 2, and the centre of motion x0 is 5. So the equilibrium point is 5, and also the amplitude is 3. So you can see the amplitude from the equation of the displacement there. So if we are starting at 5 on the number line, that's our equilibrium point, and our amplitude is 3, it means we're moving up 3 and back 3. So we're moving up to 8 and down 3 to 2. So the endpoints of our motion are 2 and 8. We also have then some examples where we have to use what we did in the last lesson, that d dx of half v squared equals the acceleration. Alright, the velocity of a particle moving in simple harmonic motion is given by that. Find the 2 points between which the particle oscillates. So remember, the particle is moving up and down like this, and it is going, or you could say moving in a straight line like this. And when it turns, the velocity is 0. So at the end points, the velocity is 0. So we can find the end points, or between the 2 points between which it oscillates, by making velocity equals 0 and solving for x. And that's easy because we've got an equation with velocity, make that equal to 0 and solve for x. So that's what I've done here. You get the 2 endpoints there. Find the centre of motion. The centre of motion will just be halfway between the 2 endpoints, the midpoint of -2 and 1. Find the maximum speed of the particle. The maximum speed of the particle, remember, occurs right in the middle of the motion there, and at the equilibrium point or at the centre. So there's the centre point, x equals -12. Sub that in to the equation for the velocity to find what the maximum speed is. So subbing that in, you get a maximum velocity of 1.5 metres per second. And then find the acceleration in terms of x. So that's where we have to use this equation here. So we've got, so starting with v squared equals 2 minus x squared, I just halved both sides, halved everything, and then I found differentiated both sides, because when you differentiate the left-hand side with respect to x, you get the acceleration, and when you differentiate the right-hand side with respect to x, you end up with this. And then we have acceleration in terms of x. And some more notes for you in terms of velocity in terms of x. And so we've got the acceleration there is -n squared x. And you know that acceleration is d dx half v squared, so that must also equal -n squared x. If we integrate both sides with respect to x, then we get this with our constant of integration. And if we just multiply both sides by 2, we get a new constant of integration. So that's why I've got to c there and then c1 there, because the c1 represents 2 lots of c. Then let's find what that constant of integration is by using the fact that at the end point, and the end point is going to be where the amplitude is, when x equals a, then the velocity is 0. So when x equals a, velocity equals 0. Sub that in to find the constant of integration, which ends up being that. Replace that back in there, and then just factorise out an n squared. And you get another expression for the velocity in terms of x. And this equation only applies when the equilibrium is at the origin, because this information here, x equals a, would only happen if the equilibrium point is the origin. Okay, so that's another important or useful formula to use and to remember. So, here we have an example using that formula. V squared equals 4 outside of 9 minus x squared. So there's the formula that I just had written down in that red box there. So you can see n squared equals 4 again. That means n must equal 2, and a squared equals 9, so a must equal 3. The amplitude is 3. The period, is 2 pi on n, so the period would be pi, but remember this is the equation for the displacement. So you've got n is 2, a is 3. So now we just need echelon, and we can find that by using the information given that the particle is initially at x equals 0. That means when t equals 0, x equals 0, sub that in and we get echelon, and then there we have find an equation for displacement in terms of time. Displacement in terms of time. And last question. A particle moves in simple harmonic motion and the acceleration is that. Initially, the particle is at rest at the origin. Okay. Show that v squared equals 6x outside of 8 minus x. So we're given our expression for the acceleration in terms of x. And we want velocity in terms of x. So replacing the acceleration with d dx half v squared, and I've just expanded this, and then let's integrate both sides with respect to x. So integrating this, we get our constant. Let's find that constant by using this information here. When t equals 0, velocity equals 0, x equals 0. Subbing that in, we get the constant, is 0. So then we have an expression for v squared, then multiply everything by 2, factorise out 6x, and you can see that's what we had to show. And to find the endpoints, remember at the endpoints, the velocity is 0, right there and right there, if our particle is moving this way. So make v equals 0, solve for x, and you can see x equals 0 or 8. That's it.